We're just gonna jump right in. We might have some time at the end that I can talk about your exam that's coming up next week. Because we've only got this tiny bit of 1.6 and then 1.7 goes pretty quickly. But we're just gonna start right away. So at the end of Wednesday, we started talking about kind of this new form for exponential functions. So we've been working with p naught a to the t, and now we're going to introduce this new p naught e to the kt. And technically, they're usually used in different contexts, and the different context depends on, whoops, I forgot to put the little pen on. I always forget that. Goodness gracious. The difference is pretty much just based off of whether you see the word continuous or not. If you see continuous, then it's going to be an e to the kt form. And if you don't see continuous, it's going to be the usual already used a to the t form. Now, even though they're used in different contexts, well, maybe I shouldn't say different contexts, but even though they're used kind of in different ways with a continuous rate versus a not continuous rate, we can always find the n equivalent equation in the different forms. So no matter what form we're given, we can always find an equivalent in the other form. And that's kind of what we stopped at last time. We did one example of it, but we've got kind of 3 more to kind of go back over it again. So the main point of it was the fact that, so here are our 2 forms right here. I don't know what this arrow is pointing to, but so we have the 2 forms here, and if you notice, the only thing that differs between the 2, say you wanted these to be the same equation, you wanted them to represent the same set of data. If you wanted to represent the same stuff, you'd want everything to be the same. So the p naughts could be the same, the t exponents could be the same. Well, then the only thing we need to make sure it turns out to be the same is we need to make sure that a is equal to e to the k. So if we allow that to happen, then these 2 things must match up. So that's kind of what we did in this first one. We let p naught stay p naught, and we set a equal to e to the k. We had e to the k, so we just punched that into a calculator. So let's see the second example of that. So example 2, the same type of idea that we ended with on Wednesday, where we already have, no, sorry, I want to jump over to number 3. I'm sorry. Jumping over to number 3, because I want to do the other one that has the e term in it first. So here we have an e to the kt, and we want a to the t. So again, p naught doesn't change. You can just let p naught stay p naught. But then we have to use this relationship that we're letting the a value be equal to whatever e to the k is equal to. Since we have e to the k here, it becomes just a factor where we just have to punch that into our calculator. You just got to take, if I didn't mention it last time, on your calculator, at least if you got a TI-84 or 83, if you weren't aware of where the E button is, what you're going to want to have to do is you're going to have to press second and then the division symbol. Well, this is one way because it's got a little E above it. Or the other way you can get to it is second and then press the natural log button. That will get you an e to the x, so it'll immediately put you into an exponent. With the one that you get from the division symbol, you then have to do the little caret to get in. Frozen and not the movie. That was a bad joke. It's a terribly bad joke. Better, Caitlin?
That's better. Thank you.
Hooray! I could barely hear that. Let me turn this up. There we go. Oh, now my screen is flipped. Alrighty, so yeah, that's kind of how you do it on a TI-83 or TI-84. But you just punch in e to the 1.2, and you get that our a value is going to be approximately 3.32. So once we have p naught and a, we have our equation. So we have p equals p naught a to the t. All right. Now these last 2 are essentially going the opposite way. So we have an a to the t and we want an e to the kt. Still, p naught stays the same. Now technically, we have this other relationship that we can just pull out. We can just set the k value equal to the natural log of a. But I personally think it's easier to remember just the a equals e to the k form because it kind of falls out from just looking at the two equations next to each other. So I personally always just use this, and then you can just solve from there. So we have the a value here, and we'd want to solve for k. And to solve for k, you would take the natural log of both sides, which is why the natural log pops into that thing that I just scrolled back up and looked at. Now remember, this comes from the natural log of e to the k, so I kind of did two steps at once there. Took the natural log of both sides and then pulled out the power of k. Now since the natural log of e is 1, we can kind of just cross that out and say that k is equal to the natural log of 1.06, which is where that thing comes from. So you ask your calculator, please tell me what the natural log of 1.06 is, and your calculator will tell you it is approximately 0.058. So we have our P naught, we have our K value now, so we can write it in our P naught e to the KT form. So we've got 500 e to the 0.058 t. So same kind of idea, it's just if you use this way, which again, I usually just do because that's the way that I remember. If you also remember the fact that k equals the natural log of a, if you want to remember both pieces, then you can kind of jump straight to a calculator punch-in step. But even if you use the a equals e to the k, you just do a tiny bit of solving and get to the same spot. Good now, Shannon? Okay, cool. All right, so same idea for number 4. Let's just go through one more example of this. So we've got 152, 0.92 to the t. So we've got an a to the t, want a e to the kt. So one more time, P naught stays the same. If we're using my way, the way I always remember how to do it, we'll have to take the natural log of both sides. Natural log of e is 1. So we just get that k equals the natural log of 0.92. Sorry, there we go. Ask your calculator what the natural log of 0.92 is, and your calculator will tell you that it is negative 0.083. So the equation that we want would be P naught of 152, e to the k value we just found, t. So this is how we're able to take one form and find its equivalent other form, if you will. Not used very often, if I'm completely honest, but if we ever need to change forms, we can. Questions, concerns on any of that before I move on to 1.7?
Yeah, can you go over 2 one more time?
Yeah, 2. So it's so little work, let me just erase it all. Boink, 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 except all the little bits take forever to erase. So P naughts are always going to stay the same. Oh, geez. P naughts are always going to stay the same. So P naught is just going to be 500. But now, once again, if I want these two forms to be equivalent, the only thing that differs is the a versus the e to the k. So I can kind of use that relationship to find the other thing I need. Well, we're given the a value here. So a is 1.06. So that's going to be equal to whatever e to the k is. Remember, e is a number, so the thing I actually want is the k value. So to solve for k, since it's in an exponent, we need natural logs. So I need to natural log both sides. And let me do it full out this time, because I skipped a step. Take the natural log of both sides, and then the point of the natural log is that you can pull the power out. the natural log of E is equal to 1. So the right side of this is literally just equal to K. So we essentially end up with K equals the natural log of 1.06, which we punch into our calculator to get that K equals 0.058 approximately, rounding. So if we need P naught e to the KT, I need a K value and I need a P naught value. I've got my P naught value, I've got my K value. So now I just plug it in. So 500 e to the 0.058 t. That makes sense?
Yeah, thank you.
Any more questions before we move to 1.7? Alrighty. Okay. So now I've got to unshare this and share 1.7. Where's 1.7? I know I have it up already. There it is. Now 1.7 is almost a little weird because we already have like 90% of the material we need to do all of these problems. There's like 2 definitions that we need to give, but everything else is just, this is essentially using exponentials and logarithms to solve word problems. So I guess it's just mainly putting the stuff we just learned into contextual word problems, I guess. Excuse me. So first one we've got is there's a spill of radioactive iodine. The radiation level was 2.4 millirems per hour, so an evacuation was ordered. The radiation decays. Oh, I always forget when it's a new page. Decays at a continuous hourly rate of K equals negative 0.004. So here's what I mean by it depends on the context which form we use. Since we have the word continuous here, we're going to use the E to the KT form instead of the A to the T form. If you use the A to the T form, you're wrong. If you use the E to the KT form and then convert over, you're right, but you've done an extra step that I don't know why you did it, but technically, whatever floats your boat. But you can't start with an A to the T form. Since it says continuous, we have to use an E to the KT form. Now, they're super nice and just essentially gave us the K value. One thing that I do want to point out, so say they had listed this as a continuously hourly rate of, what would that be, 0.4%. So sometimes they don't list it as negative, but remember that the word decays would get us that it's negative. So also just be careful to double check whether you're growing or decaying to make sure that the sign of the rate is correct if they don't give you the sign. But they gave us the sign, so that's really nice of them. So the first thing we wanted is what is the level of radiation 24 hours later? So, well, the first thing I should probably figure out is what's my equation. So I'm looking for some P naught e to the KT. Well, we're told what K is, so that's nice. Don't have to find it. But what's P naught? Well, of course, the P naught is the value we start with. And we're told that the original value of this radiation was 2.4. So we've got our equation is 2.4 e to the negative 0.004 t. So if they're asking us for the radiation level 24 hours later, what are we going to do with that 24? We're going to plug that sucker in. Take 24, plug it in for t. And punch that sucker into your calculator. Should stop saying that, but oh well. So type that into your calculator. It will tell you that this is approximately 346.57 hours. One note for anyone who has possibly an older calculator. So some of the older TI-83s, and I'm sure some other versions, I don't know. If you're typing that into your calculator, you want 2.4 e to the caret, and then parentheses. well, you could write this a couple different ways. You could put parentheses around the 24 as well. But make sure the entire exponent goes in parentheses if you have an older calculator. If you have a newer calculator, it's super nice and it kind of just makes it look like an exponent, kind of pops up on the screen. So you don't have to worry about it as much. But if you have an older calculator, make sure your more parentheses is better when you have an older calculator. But yeah, anyway, otherwise it'll give you the wrong answer. Which is also why I always ask you to show all of your work on full response questions, because if you have, you know, if you're taking an exam and you have this on your exam, but then your number's wrong, I know that something went wrong when you punched it into your calculator because you had the right calculation. So you're gonna get, I don't know, I might take off half a point because the final answer is technically wrong, but if I'm feeling mean that day. But like, you're gonna get pretty much all the points, if not all the points. Usually I feel nice enough to just be like, well, this was right and something just happened when you punched it into your calculator. Anyway. Part 2, find the number of hours before it reaches the maximum acceptable level, which would be considered to be 0.6. So now we want to solve for an hour value. So we want to solve for t. So this 0.6 is going to go in for p. So we're going to have 0.6, 2.4 e to the negative 0.004 t. And we want to solve for t. Well, whenever we want to solve for something in an exponent, that's when we've got to pull out our trusty dusty natural logs. Or, well, we've got to do a little bit before we can take the natural log. But we're using that process of solving equations using logarithms. So the first thing we always want to do is to isolate the exponential. So we need to get that 2.4 over to the other side. So we need to divide both sides by 2.4 to get it away from the exponential. That's going to give us 0.25 e to the blah, 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 0.004t. And now that we have it isolated is when we take the natural log of both sides. So we take the natural log of both sides. And if I may, I'm going to do the pull the power out at the same time. Let me know if you want to see the other step. But I'm just being a little lazy. That's kind of the point. Take the natural log, you can pull the power out. Natural log of e is 1. So since it's multiplication, I can kind of forget about it because anything times 1 is itself. So to solve for t, we would just have to then divide by that negative 0.004. Which would give us that t is approximately equal to, where is it, 346.57 hours. And I often get the question, where the heck did the negative go? Natural log of 0.25 is a negative number. So we technically have a negative divided by a negative. You just kind of don't see the one negative because it's written as natural log of 0.25. Questions, concerns on that example? So again, technically, did you write the wrong answer for part? Yeah, no, I wrote the answer for part 2 on part 1. Yeah, no, I did that wrong. Sorry. 2.18 millirems per hour. Yeah, sorry, I totally wrote that up there because I was looking at the wrong part of my notes. Thanks for calling me out on that. See, so I would have gotten it wrong on my own exam because I wrote down the wrong number. Oh, Lord. Anyway. So, otherwise, hope we're good. So, this next one, I don't see any more questions. I'll try to leave that last bit in there just in case. So the population in Kenya was 18.9 million in 1984 and 46.1 million in 2015. Assuming exponential growth, find an equation for the population of Kenya as a function of time t in years since 1984. Oh, okay, sorry. There we go. Because I want to make a note of something. It says assuming exponential growth. This does not have the word rate or the phrase continuous rate. So it doesn't tell us, so essentially, let me just finish what I'm saying here. So it doesn't have the word rate or the phrase continuous rate, so we can choose. That doesn't look like a C. If the word rate had gotten in there at all, if the phrase continuous rate had gotten in there at all, we wouldn't be able to choose. We would be forced to use whichever one it was telling us to use. But since the word rate, the phrase continuous rate, does not show up at all, we get to choose which form we'd rather use. Okay? And actually, it would turn out to be, if you, no matter which one you did, they would turn out to be those equivalent forms. Like just like we just found at the end of 1.6, you can find the equivalent form, an equivalent equation for each form. Since this doesn't specify, the process that we do would find us that kind of equivalent equation in either form. Now, technically, we've done one of these before. This is similar to that wolf example we did in 1.5, where we had 2 points and we had to write the equation from those 2 points. So since we've already done one for an a to the t form, I'm going to choose to use the e to the kt form here. Now, the process is pretty similar. Maybe I should pull that up super duper quick. That process I'm talking about to remind you guys what I'm babbling about. So super quick, I pull that up. Here it is. Unshare this really quick. Share this really quick. This guy. So essentially, we're going to be using this process on the left that I've highlighted too much of that you can't see because it's lagging, I guess. There we go. But just this process on the left for finding the equations of 2 points, finding the equation given 2 points. But instead of using a to the t, we're now going to use e to the kt. But it's the exact same process, just in a different form. So just if you're wondering where I'm pulling some of these steps from, it's that process. So the first thing we had to do in that process is to write the 2 points in the equation format. So let me see what 2 points I have. Well, I have 1894, but that's 0 years since 1894, and 18.9, and I also have 2015 is, if my notes are correct, 31 years since 1984, and had a population of 46.1. So those are the 2 points we're working with. Now, there's a tiny bit of a shortcut we could take here, and I'm going to take it towards the end. But once again, because it's not always an option to have that shortcut, I am going to do the full process partly as well. So we want to write both of these in the equation form. So we have 46.1 equals, don't know what P naught is, don't know what K is, but T is 31. And then 18.9, also remember the suggestion for this was to put the one with the higher T value on top because the next step we're going to do is division. So once we wrote them both in that format, we could divide the 2 equations. And remember, the point of doing that was to get the P naughts to cancel out because we have too many unknowns at this point. Go away. So 46.1 divided by 18.9 will give you approximately 2.43915. Let's take a decent amount of decimal points. And so this will be equal to e to the, well, I'm going to write it as 31k instead of k31. And this essentially comes from 31k minus 0, these 2 exponents. Remember, when you divide things with the same base, you subtract their exponents. So we essentially have 31k minus 0, which gives us 31k. So let me just rewrite that up here because I'll need it for the next thing. So at this point now is where we want to solve for k. We want to solve for the value that we don't have. So here, since the k is in an exponent, we need to use our natural logs. So we need to take the natural log of both sides. I'm going to pull the power out at the same time. Natural log of e is 1. You can always still divide by the natural log of e if it makes you happier. You'll still get the right answer, but it's technically unnecessary because it's equal to 1. But so our k value is going to come from this gross division, which will let you know that your k value is approximately 0.028763. So let's just say 0.02, let's take 88. Let's chop it off at 4 decimal places. And again, if I don't specify at least 2 or 3, I'm taking 4 here just because I felt like it. But always just triple check instructions to see if they specify. So now we have our k value. So the last thing we need is our p naught. Now this is where I am going to take a bit of the shortcut. I will remind you how to do it if you don't have the shortcut. So in a full version, if you don't have the shortcut, what you then have to do is go back to one of your 2 equations at the very beginning. Pick whichever one makes you happier. I'm just going to choose the 46.11. And you essentially plug in. Oh no, I ran out of space. Hold on, I gotta rewrite that. Cool. So 46.1 equals p naught. You plug in the k value you just found and solve for p naught. So if you don't have the shortcut we're about to use in 1 second, that's how you would go about solving for p naught. Maybe I'll even say solve for p naught. But we know what p naught is here, so whenever you know what it is, you should just use the value you're given. So we're given p naught is 18.9 because that's the original population at the time that we're starting in. So since we have p naught and we have k, we can write the equation. P equals the p naught value of 18.9. E to the k value of 0.0288 t. So just like with the a to the t form, these ones do get a little long and a little tedious. Both versions, one is not really shorter than the other, really. But that's how we find the equation of an exponential function when we're given 2 points. Questions on that? I do want to mention something for your homework, so I'll try to leave that up really quick, but I also want to draw something, so I need space. On your homework, if you haven't figured it out already, there's ones that look like this, and I don't know, they give you some numbers. This technically gives you 2 points. So we know how to find the equation because we know how to find the equation given 2 points. It's technically this thing right here, just with an a to the t form instead of e to the kt. So essentially the one from the wolf example that I pulled up 2 seconds ago. But this is the process that you use for that. That seems to not quite click in a couple of people's minds. They don't quite make the connection that you have 2 points. And I'm not saying that to make anyone feel bad, but you have 2 points, so we do know how to do that. It just, we weren't given one in a graph, but we were given something like that. Anyway, so there's some of those on your homework. Did I mention the other thing to you guys? I don't think I did. There's one other one. In the homework. Now I sent out an email about one of them, and immediately after I sent out that email, I found another one that I always forget is stupid, and I always mean to remove, and I never remember to do it. But anyway, and so then I felt bad because I didn't want to send another email. There is one in, I think it's in 1.5, and it's got like a bunch of different parts, and it's talking about like billion people, I think. So it's got like billion of people here, and billion people here. And then because the universe hates us, all of a sudden the last blank is in millions. Because, you know, why not, I guess. So I think the number you usually get, and well, the number is going to depend on your problem because the numbers change per person, but you should get something that looks something like this when you do the actual calculation they ask for. But then the answer that they would therefore want, so this would have been in billion people, so you would technically want to put in 85. If you've already gotten to that question and you already lost points because you didn't realize the unit change, just email me and I can fix it. Again, I always mean to remove that question. I always forget. But I forget what number it is. But if there's like a bunch of blanks and it's talking about people and it's talking about billions of people, it's going to switch to millions because, you know, why not make life more difficult? All right. So this next set of definitions is kind of the new, one of the biggest pieces of 1.7 that we didn't already know. So we have the doubling time. Doubling time of an exponentially increasing quantity is the time required for the quantity to double. So essentially you get double of what you started with. It's always in regards to what you started with. And then the half-life, if you know any chemistry, you might have seen this before in your life. The half-life of an exponentially decaying quantity is the time required for the quantity to be reduced by a factor of 1/2. So what you start with is now cut in half. How long does it take to have half of what you started with? And of course, doubling time is only in terms of increasing things because you can't have, if you're decreasing, you can't double. And if you're increasing, you can't be cut in half. So that's why there's the specification of increasing and decaying for these. But so let's see this example of this is a half-life question. So the release of chlorofluorocarbons used in air conditioners and household sprays destroys the upper atmosphere. The quantity of ozone is decaying exponentially at a continuous rate of 0.25% per year. What is the half-life of ozone? So once again, we have the word continuous showing up here. So we want a P0 e to the kt situation going on. We're told that the continuous rate is 0.25%, so that would turn into 0.0025. But I'm also missing something else. I'm not done my rate yet. If I reread this, it tells me that it's decaying exponentially, so that rate needs to be negative. So all I have right now is K. And you might say to me, sorry, my English just started to break. You might ask me, well, what's P0? We don't know what P0 is. For half-life and doubling time questions, you don't need P0, and I'll show you why in a second. If it really, really bugs you to not have a number for P0, pick your favorite number, plug it in for P0. It's technically not great mathematics because we don't know what it is. But for the sake of solving for half-life and doubling time, you technically can choose whatever number you want. But you can also do it generically too, because here's the point. So far the only part of the equation I have is this. Because I only have K. I don't know what P0 is. But I want to know how long it's going to take for my initial thing to be cut in half. How long is it going to take until I have half of what I started with? Well, why don't I just set it equal to whatever the heck half of what I started with is? So even though I don't know what that number is, I can just say let it be equal to 1/2 of whatever it should be. So whatever that number was, I want it to be cut in half, so that's cut in half. And the reason we can do this is because we want to solve for t. We want the time. Well, if we want to solve for t, then we have to use our process of solving equations using logarithms. So we've got to isolate the exponential. So the first thing we have to do is divide both sides by P0. So the reason we don't care about what P0 is because in the first step of solving, the P0s all go away. They all cancel out. We're just left with 1/2 equals e to the negative 0.02, nope, one more zero. 0.25t. So this is why we don't care what the initial condition is for half-life or doubling time questions. Once you've isolated the exponential, that's when we bring out our natural logs. I'm going to bring the power out at the same time. Natural log of e is 1. To solve for t, divide both sides by the negative 0.0025. Punch that sucker into our calculator. You're going to get that t is approximately 277.259 years. And again, it's positive because the natural log of 1/2 is a negative number. The natural log of anything less than 1 is negative. So don't freak out if you see negatives, quote unquote, disappearing. If you have a negative, but you don't think you had a negative in the top number, it's probably because you're taking the natural log of something less than 1. Questions, concerns on that? The only step that changes if this were to be a doubling time question, so we would have had to have a different equation, we would have had to have it be an increasing equation. But the only step that's different is that instead of using 1/2, now I don't know why I used Q naughts here, but instead of using 1/2 Q naught, you would instead set it equal to 2 Q naught because you want to know the time it takes for it to double. So it's the same process where we don't care what the initial condition is, we just set it equal to twice of whatever we started with. And again, if you prefer having a number in there, go right ahead and plug a number in there, but you don't need it. Otherwise, the process is completely the same. Questions, concerns about half-life and doubling time? Because we've got one last kind of mini topic. All righty. Nope, this way. So the last little piece is to talk about this specifically in the context of interest. Now for this class, we're only going to look at 2 types of interest, kind of the simplest types of interest, if you will. There's a lot more when it comes to interest, but we're just going to focus on 2. So if the amount P naught, so you deposit some initial amount into an account paying an interest rate of R per year, and P is the balance after T years, we're going to kind of have 2 choices depending on which type of interest we're talking about. We can talk about if the interest is compounded annually. And we can talk about if the interest is compounded continuously. Here's the 2 forms. For annually, we have P naught 1 plus R to the T, which should look very suspiciously like an A to the T, since A is equal to 1 plus R, which is not a coincidence. And then continuously, now with continuously in terms of interest, it's usually written as RT because a lot of people will even they'll even just say PERT. You just use PERT. So if you've heard PERT before in your life, that's probably what they're referring to. But so the only difference from this and the other one we just looked at is that there's a difference of R versus K, but variables, you can name whatever you want. So it's kind of just, you know, the same 2 things we've already been talking about. If it says continuously, it's the E form. If it doesn't say continuously, it's the other form. So we kind of, this is kind of why this is like a, just kind of side note for the context. But so say we wanted to do these quick few examples with this new context of interest. So say a bank advertises an interest rate of 2% per year, which I changed it to 2% from last year because 2% was actually a decent one, and now it's like nowhere has a 2%. No bank has 2% interest right now. But anyway, if you deposit $10,000, how much will you have in 3 years if it's compounded first annually and then continuously? So for the annually, I need some P naught 1 plus R to the T, where we're told that we deposit $10,000, so that's our P naught. Our rate is 2%, so 2% as a decimal would give us 0.02. And we want to know the value after 3 years. So just for giggles, I'll write 1.02. But punch that sucker into a calculator. And that's going to result in approximately $10,824.32. Hopefully that worked. Usually it works, so I'm going to assume it did. Just tell me if it didn't. And then if we want to look at it continuously, if it's continuous, then we're in the P naught e to the RT form. So P naught again is 10,000. R is still 0.02, but here we don't add 1 to it. There's no adding 1 in these cases, in the E case, and we want to know after 3 years. Well, remember, E is just a number, so that's just something you punch into a calculator. So we've got $10,832.87. And now I might actually talk about the difference between the two. So interest annually means that you're just getting interest paid at the end of the year. So however much interest you're getting, it's just getting paid at the end of the year. Whereas continuously, and so you can also have like monthly interest, daily interest, hourly interest. Those don't really happen a lot, but monthly interest is usually the thing. But anyway, continuous interest would technically be you're getting interest every single possible millisecond possible. So it's just continually creating interest and adding it in. So you're kind of getting that interest every single possible moment in time. So when it comes to, you know, if you were to ever have a choice of continuous interest, you would always want to choose it because the more often it accrues the interest, the better it is. Because once you add on a little bit of interest, then your next interest is going to be slightly bigger because you have just the tiniest bit extra money in there. So the more times it compiles, the better. It doesn't really show up for low values. I know 10,000 doesn't sound like a low value, but in terms of money and interest, it is. So at this point, it doesn't seem like a huge difference between $24 versus $32 after the 800. But of course, it does make a difference. But anyway, that's kind of the difference between the two is just how often is the interest actually being added on to the amount? Is it at just once per year or is it every single possible moment possible? So our last one, and then I can babble about the exam for just a little bit, or people can leave, I don't care. So if $10,000 is deposited into account, paying an interest of a rate 1.5% per year, compounded continuously, how long does it take for the balance to reach 12,000? So we're using the E to the RT form again. Well, what's the initial value? How much did we deposit? We deposited 10,000. Our rate is 1.5%. So 1.5% is 0.01. Yeah, 0.015. This is, of course, increasing because it's interest, so it's adding on, so that stays positive. So 0.015 T. And so we don't know the time, but we're asked how long it's going to take to reach 12,000. So we want to set it equal to 12,000, of course. And now we're in a situation of solving an equation using logarithms. So again, 1.7, we kind of had most of the pieces. We just had these new contexts. So solving this, always isolate the exponential first. So divide by that 10,000. That gets you 1.2. Take the natural log of both sides, bring the power out. Finish solving for t. Natural log of e is 1, so I always drop it. So it would take approximately 12.1548 years for this to just sit in a bank and gain $2,000. But that is the end of 1.7. So we are done notes for today. I'm just going to stop there. It's not worth taking the next 5 minutes to try to do anything else. So a couple things. So next week on Monday, we need to cover at least part of 1.8. So Monday is going to be used to cover 1.8. It might not take the entire time because I'm not going to cover the entire section, but there is one piece that we need to be able to then use in a later chapter. So if we have extra time, I would love to spend it, going over some review or whatever. But I am pretty much finished, I think, creating a review. So I will be posting that review on Blackboard, hopefully later today, possibly not until Saturday morning, but it'll be up semi-soon. So there will be a review packet. It's got a list of the topics you're going to want to need to know, and then it's got some problems. So do as many of those as you think is helpful to you. Some things about my exams. I think actually someone already asked this today, didn't they? No, that was my other class earlier. So people have been asking me what's better to study from, Wiley or like the quizzes. So if you think about the type of things I give you in the warm-ups and the quizzes, those are written by me, and so is your exam. So looking over your quizzes and thinking about the warm-ups and also looking over this review packet is what I would suggest doing first, because those are going to be similar to the exam because they're all written by me, whereas Wiley is written by Wiley. I'm not saying that Wiley can't be helpful. Looking over those is definitely helpful as well. But if you're running short on time, I definitely would suggest looking over the packet that I post first. Of course, there's SI sessions that you can always attend, ours or other people's. I have 2 SIs. One of them for this class is Emily. If Emily's sessions don't work for you, I have another SI, Zach. I'll post his information on Blackboard if you want to go to his session as well. You can always find it if you just Google USC SI sessions. You can find all of the SIs, and he runs my other session. So if Emily's sessions wouldn't work for you, you can always go to Zach's or anybody else's, but Zach specifically handles classes of mine. Anyway, what else about the exam can I babble about? The makeup of it is going to be multiple choice and completely fill in the, completely, what am I talking about? Free response. And in the free response, there will be some that look like find the error, and those are on the review sheet, so you might want to look over those. It's essentially like, here's a problem, here's the work, you need to find where the error is and tell me what's wrong with it. So there will be some like that, and then just some, quote unquote, normal full response. So kind of the problems that you see on the review are kind of the types of problems, layouts that you would see on the exam. So Emily says that she's going to have a test review next week, but the day is still to be determined. She'll send you an email out when she figures that out. And again, I'll post Zach's thing in Blackboard in case Emily's doesn't work for you. I think that's all the things that I can think of. If you have any questions about the homework or the exam, feel free to stick around for a few minutes. Otherwise, have a great weekend. See y'all on Monday, and your exam is on Wednesday. One more thing I'll say before all of you leave. If you are physically able to come to campus, I will be expecting you to be on campus on Wednesday, okay? If you're isolating, if you're quarantining, that's different. But if you are physically able to come to campus, I kind of need you to be on campus. Technically, your assessments are supposed to be taken in person. I've been pretty nice about the quizzes, but technically the assessments, and with the exams being quote unquote more important, I really need you to be there if you are physically able to be there. All right, that's all I'll say. Email me if you have any questions or concerns, or stick around for a couple seconds, because I'll be here for a little while. I got a meeting in a little bit, but I can stick around. Otherwise, have a great day, have a great weekend. Blah, 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 blah. I should stop the recording.